Hello, welcome to another module in this massive open online course. So we have looked at the traditional presentation of a convolutional code. Let us now look at the principle for the decoding of a convolutional code. So let us look at the decoding . Or rather the principle involved. Okay. So let us say we have a received code word R bar, which is given as 11 11 10 0 1 1 0 1 0 1 1. So this is basically R bar at time instant 0, R bar corresponding to time instant 1, R bar corresponding to time instant 2, R bar 3, R bar 4, R bar 5 and R bar 6. Okay, and we have to, decoding means basically we have to find the corresponding, and we would like to find the corresponding decoded code word. Okay, C0 bar, C1 bar, C2 bar, C3 bar, C4 bar, C5 bar. Now note that this is the received code word, correct? This is the received code word. Now note that we have said that any legitimate code word corresponds to a path through the trellis. But this might not be a valid code word. It's important to note that this might not be a valid code word. This is important to realize. The received code word might not be a valid code word, reason being due to errors over the, or due to errors introduced by this. That is the whole point of introducing coding, right? So we are transmitting a valid code word, but what you receive at the receiver in this digital communication system might not be a valid code word, because the communication channel can flip some bits. Once you flip some bits, it is not guaranteed to be a valid code word anymore. So corresponding to the received code word, we have to find a valid code word that has been transmitted. But this is the challenge, which means we have to recover the errors that have been introduced by the channel. And as we have seen, it might not be possible to recover or to basically correct all the errors. So recover or decode this received code word, in the sense that decode this received code word to the best possible extent. Okay, find the code word. So decode implies find a valid code word, correct? Now a valid code word, obviously we said valid code word means corresponding to corresponding to a path in the trellis, but there might be many valid code words, right, because there are many paths in the trellis, so any of them can be a valid code word. So how do we decide which is the valid code word? The point is, we want to decode the corresponding code word to the highest, to the most, to the basically the most possible extent, correct? I can say to the to as accurately as possible. So decode it as accurately as possible. Okay. Decode as accurately as possible. Now, how to observe, and now how do you decide which code word is the most probable code word? So what we want to do is, somehow we would like to come up with a metric. When you say as accurately as possible, you would like to come up with a metric to decide the most probable code word that could have been transmitted. Now, the most probable code word that has been transmitted, okay, or basically the most likely, or another way of stating this is the most likely code word to have been transmitted. Or the code word with the maximum likelihood. The transmitted code word with the maximum likelihood. And to find that, we want to define what is known as the Hamming distance. We want to define the Hamming distance. Hamming distance is nothing but the number of bits of dissimilarity. This is equal to number of bits of dissimilarity. The Hamming distance between two code words is the number of bits of dissimilarity between two code words. For example, okay, for example, we have code word 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 0, 0. Look at this, there are 2 points of dissimilarity, 0, 1 and 1, 0. So we can say 0 has been flipped to 1, 1 has been shifted to 0. So 2 bits are dissimilar. So let us say this is C1, this is equal to C2, or still better, to allude to why we need this, let us denote this as the received code word R. This is the corresponding any code word C bar. Okay, so there are 2, okay, 2 dissimilar bits. This implies Hamming distance, which we will denote by DH. The Hamming distance DH is equal to 2. Okay. Now the principle is clear. The most likely code word, that is a maximum likelihood estimate of the transmitted code word, is one which has the minimum Hamming distance from the received code word. We are not going to rigorously justify this, but it's intuitively clear. We are basically trying to find a code word, but not any code word, because there are several possible code words that can be generated by the trellis. We are interested in finding that code word which is as close as possible to the received code word. So the decoding principle can be further stated more precisely as that is, we want to minimize the Hamming distance between R bar, received code word, and C bar. So DH is, remember, DH is the Hamming distance, R bar is the received, R bar is the and received word, and C bar is the, okay. So we want to find that particular C bar which is the closest, which has the minimum Hamming distance with respect to the received word R, and this principle, that is termed as the maximum likelihood decoder. This principle is termed as the maximum likelihood decoder, and this estimate C bar, the code word estimate C bar, is termed as the maximum likelihood estimate, or this is a maximum likelihood decoder, and the C bar so found is termed as the found from this decoder is the C bar so found is the maximum likelihood estimate. Okay. Now further observe that this Hamming distance metric which is basically the number of points of dissimilarity, number of bits of dissimilarity, this is additive. This is the Hamming distance between C0 bar, R0 bar, plus the Hamming distance between C1 bar, number of dissimilar bits between C1 bar, R1 bar, so on and so forth. That is basically summation I equal to 0 to n minus 1, where n is the block length, the Hamming distance between Ci bar. So this Hamming distance metric is additive. That is, the total Hamming distance between the code words can be found as the sum of the constituent component Hamming distances. So this Hamming distance metric is additive. This Hamming distance metric is additive. Okay, distance metric is additive in C bar I, comma R bar I. Okay, so you add the Hamming distances of the various components between, that is, if you look at each time instant I, C bar I and received code word R bar I, you take the Hamming distance, correct? You add all these Hamming distances, you get the overall Hamming distance between C bar and R bar. Okay, that's an important point. It's a very obvious point, all right. It's very obvious and intuitive also, but it's very important, all right, to realize this. Okay. And because this is going to lay the foundation of the decoding procedure that we are going to illustrate subsequently. Okay. So observe that, now observe, now comes the important observation. Observe that C bar I corresponds to a branch, each code word C bar I. So for each branch we have a generated code word C bar I. So C bar I corresponds to a branch in the C bar I corresponds to a branch in the trellis at the ith stage. This basically implies that D of C bar I comma R bar I can be designated as a branch metric. That is the important point. This can be designated, thought of as a branch metric. So I have Ri, and for any branch in the trellis, that is at the ith stage, I have several branches. So I have states at I minus 1, I plus states I minus 1, states at I, several branches going from I minus 1 to I. So each branch corresponds to a certain code word C bar I. Alright, I can look at the distance between C bar I and R bar I, and I can designate the branch with this Hamming distance. This is denoted by the branch metric. Okay, so I am just writing the distance here, but it should be obvious that we are considering the Hamming distance. Okay, I am not going to explicitly keep writing dh, but all such distances are the Hamming distance. So we are going to consider only the Hamming distance. Okay, because our optimality criteria and everything is in terms of the Hamming distance. Okay, and therefore for the optimal minimum distance, and now we have seen that total distance. So now you can see the total distance, that is dh bar. This total distance is sum of the branch metrics, because each of these is a branch metric. Okay, that's what we have seen. Each of these is a branch metric. Okay, so each of these is a branch metric, and so this overall Hamming distance is basically nothing but the sum of branch metrics. So basically decoding implies, therefore for optimal minimum distance code word, for the optimal minimum distance code word, we have to find a path through the trellis such that the sum of the branch matrix is minimum. That is the point. Find a path through the trellis such that the sum of the constituent branch matrix is minimum. That is the point. Okay, so we have to find a path through the trellis such that this path has a minimum. So what we are doing is very simple, or what we are going to do is basically denote each branch in the trellis with a branch metric. This branch metric is the Hamming distance between the code word that is generated by that branch and the received word at that time instant. And now we have to find a path through the trellis such that the sum of its branch metrics is minimum. That corresponds to the minimum Hamming distance code word that is generated, that corresponds to the code word which has the minimum Hamming distance with respect to the received word. Therefore, in turn this code word is the maximum likelihood estimate, or corresponding the maximum likelihood estimate of the transmitted code word corresponding to the received code word R. And therefore, now our task is basically simple. We have to find, because we said that any valid code word corresponds to a path to the trellis, we have to find a path to the trellis. Now there are many paths to the trellis. We want to find the path through the trellis which has the minimum metric. What is the minimum metric? Hamming distance, minimum Hamming distance with respect to the received code word. And that minimum Hamming distance can now be split in terms of the Hamming distances of the constituent branches of this path. Okay, and therefore we want to find that path which has the minimum overall metric, and that is what we are going to do in the subsequent modules. Thank you very much.